Hello there. Welcome to our science lesson today. The topic for the day being particles in elements and compounds. Subtopic being chemical elements. In our previous topic, we looked at the various elements where we had to identify the elements in terms of the chemical symbols. We also looked at when the elements were discovered and by who. In addition, we looked at those elements in respect to their uses. Just maybe to do an overview of some of those elements, the scientists who discovered and their uses is, we discovered that there are elements which we cannot pinpoint out the particular person who discovered the element. These are elements that were used in the ancient world. These include elements like iron, which was commonly used in the smelting of weapons early enough, and also tools to be used in various ways. We had other elements like copper, which also used in the same fabrication of tools by the early people. We also have an element like lead and the others. So these are elements that we cannot pinpoint out the particular scientist who came up with the element. However, we have those that we can categorically pinpoint a particular scientist who could have come out with that particular element. The first element being discovered being hydrogen as an element, hydrogen. This is an element that was discovered by a scientist by the name Henry Cavendish, and we also need to know the time at which or when the element was discovered, and that comes out to be in 1766. So the first scientist to come up with an element, at least the one we can pinpoint out, is Henry Cavendish, and that is in 1766. So just like what we did previously, you can go on and list out all the scientists, the year in which a particular element was discovered, and even the uses associated with that element. For example, for hydrogen, you can discover that hydrogen can be used as fuel. Can be used as fuel. When you combine hydrogen as hydrogen gas and oxygen, particularly in machines like rockets, they use hydrogen and oxygen, which is compressed so much to acquire a liquid of oxygen and a liquid of hydrogen, and when they combine, they produce a lot of energy, giving out that energy and water as the byproduct. So hydrogen here is being used as a fuel, and so many other uses. We also talked about maybe in industries, you want to make margarine, you can use hydrogen gas to harden oils. So when you have oils and you are passing hydrogen gas through it, in a process we call hydrogenation, you discover that hydrogen gas causes hardening of oils to come up with the fats, and some of those fats are margarine. So in the same spirit, today we are to continue with these chemical elements and looking at the chemical elements in more details, depending on other characteristics that are associated with the so many elements we shall be encountering. So we also need to realize that as much as we have 118 elements in the periodic table, and out of these we have a slightly big number of the same, that is 92, being elements that can easily be pinpointed at any single moment So these ones are naturally occurring. Naturally occurring. So we can have these ones as the ones you can get at any single moment you are looking for. But out of the 118, we also have others that occur at very limited time. And they mostly occur when we have things like radioactive decay. Remember, in radioactive decay, the element that is undergoing the decay breaks out and gives out other different elements and other particles plus energy, and those other particles will be of different elements, and some of the elements will have a very short, what we call half-life, making it to be rarely occurring. But the 92, we can always get them. Now, out of these 92, we can also categorize out these elements in terms of occurrence in the Earth's crust. At what percentage can you get that particular element? So out of our 92 naturally occurring elements, we can have the following as elements that will occur in relatively a bigger percentage. The others occur in very small percentages that we shall just place in others. Elements like gold, and that's why it is a very precious substance on Earth, being sorted out by so many. Silver also being sorted out by so many. Those ones will make a small percentage that we shall call others. However, we will have those that occur in very large percentages. And the first one is oxygen. Oxygen occurs in two different ways. One, it can occur as oxygen gas, naturally as oxygen gas. And it is the gas that makes me and you to live. Because without oxygen, biological systems in our body cannot function. That's why you breathe in, have the oxygen, so that you can have the so many things that happen in your body, as you have learned in biology, happen. But in addition, this oxygen can also be found as a compound. Remember, we are now looking at elements and compounds. So it can also be found as a compound. In a compound form, it means this oxygen is found combined with the other elements, forming different substances that will be carrying different names, that will be carrying different behaviors, properties. But even if they have different properties, they still have in that compound oxygen. A good example is even carbon 4 oxide, what we also call carbon dioxide, carbon 4 oxide. You can see these are compounds where you have carbon and oxygen having come together to form a single substance by the name carbon 4 oxide. Another one, you can look at it like iron oxide. Iron oxide, where you can go purify and get out iron, which will be used in so many ways as iron metal. But you don't just get iron as iron metal. You get iron as an ore, which is in most cases an oxide. Now, this iron exists in two oxidation numbers. So you can have this one which is showing oxidation number of 2, and you can also have this one where the oxidation number of iron is 3 and that of oxygen is 2. So here we have no number being given because the oxidation number of oxygen is 2 and that of iron is 2, so they cancel out. But here we cannot cancel out because 2 and 3 are two different elements. So in this case, you are seeing oxygen existing as an oxide. Now look at the so many elements we have on Earth. There's so many oxides we have on Earth. There are so many. And these just prove that surely oxygen is the element that has the highest occurrence on Earth, which is about 46.6%. So here we are seeing 46.6% occurrence of oxygen in the Earth's crust. Here we can now see oxygen having highest occurrence, and the occurrence being 46.6%. The second element in terms of occurrence is silicon. Silicon is our second element. Silicon also occurs as silicon, an element, but it also occurs as silicon, a compound. Silicon as a compound is found in the Earth's crust as silicon oxide, which is silicon oxide, whereby in this compound form, it is what makes the biggest junk as sand. So when you talk about pure sand, you are more or less talking about silicon oxide. But here our big interest is which element is present in that compound. The compound we are calling silicon oxide or silicon dioxide. Coincidentally, you can also see, in addition to silicon being present in that oxide, we also have oxygen, just as we have mentioned up here, that oxygen has the highest occurrence by percentage. But you can also see silicon is there. And look at the Earth's surface. Sand is almost everywhere. Though we have some areas where you cannot pinpoint the sand, but a large chunk of the crust is having at least sand. And what is sand? Is silicon oxide, which is a combination of silicon as an element and oxygen as the other element. The percentage composition of this one is 27.7%. 27.7%. That's a very big percentage. Now, looking at the two keenly, you discover that these are not metals. They are non-metals, giving us a conclusion that the biggest part of our Earth crust is made of non-metals. And the non-metals mainly are these two, that is oxygen and silicon. Let's do a calculation and find a combined percentage of these two. This is 13, carry 1, this 13 plus the 1, 14, that is 6, 7. So we are having a combined percentage of only these two, oxygen and silicon, at 74.3%. So you can roughly put non-metals percentage occurrence at around 75.0%. Why add on maybe the 0.2% so that you can reach 75%? The answer is we also have other non-metals that will always be found in the Earth crust, but in smaller percentages. So if you can have all of them put together, then can take us to that. 75.0 is not an exact percentage, is only but an estimated percentage, where we are putting into consideration the big ones plus the others that will be existing in smaller percentages. The third element that has the highest occurrence is aluminium, which is written as Al, and L, we have to be careful on how we write the L. So aluminium, this one becomes the first metal on the list, but in general is the third element. And aluminium can exist in most cases. In most cases, it exists as a compound, where it will be in a compound form with, in most cases, oxygen, forming ores where you can extract and purify it to get aluminium as a metal. So in a combination with the oxygen, the oxidation number for aluminium is 3, and that of oxygen is 2. So forming aluminium oxide. Aluminium, whether in pure form or in compound form, it gives a combined percentage of 8.1%. So I've begun the metal part. This was the non-metal part, but here we also have the metal part. So number one being aluminium at 8.1%. The second, the fourth, but the second metal is iron. The fourth element, but the second for metals is iron, which also exists in most cases as a compound, an oxide. So you can see most of the elements are going in for oxygen to form compounds, and iron can exist as iron 2 or iron 3 oxide. Iron 2 or iron 3 oxide. In whichever way, it will still be iron existing, and iron in this case gives a combined percentage of 5.0%. 5.0%. The fifth element, which is the third for metals, is calcium. Calcium as an element written as Ca. Remember, A must be smaller in size than C. And it also exists in a compound form. It does not mean that they all exist as oxides. They can exist in different ways. Remember, calcium is commonly found in limestone. Limestone is occurring in so many areas, which is normally extracted so that cement can be made. All or most of the buildings we are residing in are in one way or another using or having used cement in construction. And if you look at how cement is made, calcium carbonate, which is limestone, that is calcium carbonate, which is limestone, is a bigger component of it. So in the calcium carbonate, you can see we have calcium as an element, we have carbon as an element, and the big one, oxygen, is also present as an element. Here, calcium, either as pure calcium or calcium as a compound, gives a combined percentage of 3.6%. 3.6%. So you can imagine there's so many vast areas where you can extract limestone, which are so many from different countries, even some in the seas, in the corals. If you look at the composition of the corals, you'll find that there are a bigger part of it being calcium carbonate, but they only carry 3.6%. So this shows that these percentages, as you can see them, they are not small. They may appear as a number small, but in reality, this shows a very big part of the Earth's crust. The sixth element we can look at is sodium. Sodium as an element. Sodium also is found in compound form. It cannot be found in pure form naturally because of, in fact, being a very reactive element. There is no way it will be left that way. It will always react until it forms a more stable compound, and therefore sodium is always found in a compound form. Now, in compound form, we have things like wood ash. Imagine there's so much firewood being used all over the world. Firewood. When you burn firewood, you form ash. When you look at ash, if you can make a solution out of the ash, if you can make a solution out of the ash, what you can call wood ash solution, and you test it, you will discover that that solution will be alkaline. And if you go further to test and identify which type of alkaline you are talking about, you discover that that alkaline will be sodium hydroxide, sodium hydroxide or potassium hydroxide. Then what does this one tell us? It tells us that then in that wood, a very big chunk of it could be that sodium and even potassium. A very big part of it will be sodium and potassium. So these two also carry a big portion of the Earth's surface, because for you to burn that wood to give you that sodium hydroxide or give you that potassium hydroxide, then it means this plant had to get that nutrient, that element from the crust, our Earth's crust, meaning that we have plenty of it. To confirm this also, when you are burning wood, how does it burn? Which color of the flame is produced? You find that the flame produced is usually yellow in color. Now that yellowness of the flame is partly because of the color produced during movement of electrons in the sodium metal. So when an electron moves from a higher energy level, outermost energy level, to a lower energy level, which is innermost energy level, the energy that is having is lost, is given out as light. So by losing that energy, you go lower where you require less energy, and that energy is given out as light energy. Now that light will be yellow in color, which is a characteristic color for sodium as an atom. In fact, it is normally called that test, flame test. So if you do that, you see a yellow flame or a golden yellow flame, then you can comfortably conclude that whatever you are burning or heating should be a substance that contains sodium ions. So for sodium, the percentage composition here is 2.8, and for potassium is 2.6. This one is also seen during burning, whereby you discover that the flame, though it is yellow, some parts may appear purple, lilac. Purple or lilac, they all work well in describing the color given out by potassium as an element. That is just to confirm that surely in addition to that sodium being present in that piece of wood, we also have potassium, which is a very good percentage being present in that particular piece of wood. Then the last one we can talk about is 8, and that is magnesium. Magnesium is also a very important element in our lives. It is also found, magnesium is very important in our lives. It is also found as a compound, and more so in plants. This magnesium is the center point of forming chlorophyll. And as you learned in biology, you discover that without chlorophyll, there is no photosynthesis. Without photosynthesis, there is no food. And therefore, in conclusion, without food, there is no me and you. Meaning that your life, my life, starts from here. Magnesium. Where you discover that magnesium being a center point element, it is normally used in making chlorophyll, just like in our blood as human beings, or in general as animals, we require iron as a central element in forming hemoglobin. So for animals, hemoglobin center element is iron. For plants, magnesium is center point element in making chlorophyll, which are important in either of the two existence. So the composition by percentage of magnesium is 2.1%. Then doing a total of all of this, Remember, this one was a relative percentage. So going by this percentage, then plus all this, we need to reach 100%. You'll discover that we shall have a deficiency. Where does the deficiency come from? So the deficiency comes from our number 9, and our number 9 here will be other elements. So we have other elements. Other elements here, I gave an example of gold. You know how rare gold is, and being rare has made it to be a very precious substance. Each one of us is chasing after it. Silver, platinum, these are very expensive elements that you can talk about. Also on this list, you can see there's no copper. As much as you may think copper is so much, it's not as such. So you can see on this list, we have also to include copper. Look at elements like uranium, which is very important in what when we talk about nuclear energy. Electricity is not enough, or source as a source of electricity in the world. So we have to look for other ways on how we can get electricity, not just through hydro, or maybe where we can get steam from the underground, that is geothermal energy. They are not enough. Wind energy, not enough. So we have to back up the source of energy by using radioactivity. But look at the elements involved in radioactivity. As much as they may appear to be so much, polonium, uranium, they are not enough, and they will be categorized in others. We also have lead. Lead is very important. You remember we gave examples of places where you can find lead being applied so much, and one of the examples was in car batteries. Imagine the so many vehicles we have in the world. Each one of them must at least have a battery to ignite the engine, but still it will be put into the categories of others. So the others gives us a combined percentage of about 1.5%. 1.5%. And as I had said earlier, don't be maybe swayed by the percentages you are seeing, like 1.5, and you imagine these are small figure. It is so big, and if you want to find how big it is, in your geography lessons, you can find out the relative mass of the earth crust, of the whole earth. Then calculate 1.5% of it and see how many tons you will be talking about. And that is how small or how big, depending on how you will have interpreted that figure of yours after calculating the percentage by mass of 1.5 of the earth, the whole earth. Now, we have talked about so much about the chemical symbols, the chemical elements, and in the chemical elements we have talked about the chemical symbols, the elements themselves, uses, occurrence, and here now we have looked at the percentage occurrence of each one of them and how they occur. Just as a way of finding out how much you may have gotten in this lesson, and even partly from our previous lesson, I would like you to carry out a simple exercise. The simple exercise here is, there are two questions we are going to look at, and the first question is, I would like you to fill the following table. You will create a table, and the table should have columns as follows. We need to see the element. The second one, we have to look at the symbol of that element. Then we have to identify the scientist that discovered the element. So the scientist involved in the discovery, scientist who discovered that element. Then when was it discovered? Who discovered? When was it discovered? And uses. So you can give at least one use in each case. So you identify the element, the symbol of the element, the scientist who discovered, when was it discovered, and at least one use of that particular element. Now, let's go through the exercise. This is our question number 1. We complete the table by identifying the element, the simple scientist who discovered, when, and uses. To start with, we have to realize that there are elements we mentioned that they cannot be pointed to a particular scientist. So it will be good we start with those ones. And these ones include lead. We also have one here. We have iron, copper, just to name those 3. So starting with the lead. Lead, the symbol is capital letter P, small letter B. Look at the way I have written. It must be written this way. The element here is lead. The symbol is capital letter P, small letter B. This, the scientist who discovered here is dash, because it was used by the ancient people and we cannot pinpoint to whoever. And when it was used in the ancient world, you can either fill in as used in the ancient world, or you can not pinpoint to any particular year, because ancient world is a very big range of years. Then we can also look at the uses, and uses here I've just mentioned a few minutes ago that it is commonly used in making car batteries. Remember, you always need a source of energy, electrical energy, to ignite your engine. The second metal will be, or element will be, copper. Let's have copper. Copper is written by simple as Cu. Remember, they should not touch each other, and the U must be small letter U by size and appearance. If you write copper as copper, that is wrong, because as much as this U is smaller in size, by shape is capital. Remember, chemistry and English are 2 totally different subjects, and you don't interpret this one in English way. In English way, it will be said to be correct, but in chemistry way, this is wrong. So the best way to write copper is the way it is written up here and not down here. When was it discovered? Similar to lead, it was used in the ancient times, so we cannot pinpoint. And uses, this is a material or a substance or a metal that was commonly used in making coins, that's money, but can also be used in making electrical wires. Maybe to pick on another ancient based element, may I pick an metal? We also have carbon. At least I'm picking on an animator. Carbon. Carbon is written as capital letter C. By simple, scientists discovered ancient, and uses carbon is used in different ways. One of it we said as graphite. Remember, graphite is pure carbon, but it is only the issue of connectivity that gives us the difference. So as graphite, it is used as a lubricant in heavy machines. Remember, in heavy machines, like when you are drilling very big holes, fitting in big pipes, the heat energy generated when the gears are turning is so high that you cannot use any other lubricant. It will evaporate and go. So what we use is graphite, which is carbon, pure carbon. So that's one of the uses as a lubricant. It is also used as an electrode, as a connector, because as graphite, it also conducts an electric current. So you can use it as an electrode. As a diamond, remember, diamond is also pure carbon. It is used as an ornament. It is a precious stone. So I'm sure if you are given such as a gift or a present, you will be feeling very happy because of how much emotions we attach on diamond. So that's a use. Now, looking at the elements that were at least discovered by particular scientists, I will start with the hydrogen. Hydrogen. Hydrogen as an element is written by simple as capital letter H. And as an element, it was discovered by a scientist called Henry Cavendish. Henry Cavendish in 1766. 1766. Uses, I had mentioned this earlier in the lesson, and I say that hydrogen is used as a fuel. In particular, we can pinpoint to rockets where hydrogen and oxygen cylinders are carried, and they are used to power the rocket as it moves very fast, carrying so many good things into the space like satellites. So you can see hydrogen there as a use. It can also be used in hardening of oils in the process of making margarine. The second element is oxygen. Cannot mention hydrogen and fail to mention oxygen because these two elements are like twins. So the second one is oxygen, which is written as capital letter O. It was discovered by a scientist by the name Carl Skill. Carl Skill did this work of identifying this element as oxygen in 1772. 1772. Looking at uses of oxygen, one will obviously complement the one of hydrogen, where you are using it as fuel. So it is used in burning fuel. It is used in burning fuel, that is burning hydrogen, a gas. It can also be used by people with difficulties in breathing. You go to a hospital, somebody has a difficulty in breathing, you will always borrow the uses of oxygen by having those cylinders produce the oxygen and give pure oxygen to the patient so that we can keep the person alive, and so many other uses. The third element, which was discovered in the same year, is nitrogen. Nitrogen. Nitrogen is written as capital letter N, and this one was discovered by two scientists who are working on it in the same year, that was 1772, same year. And the two scientists who who worked on this were Joseph, Pierre, and Rutherford. Joseph and Rutherford were the two scientists who came up with this element, nitrogen. And nitrogen has one very unique use. Nitrogen, being that it can easily liquefy, but at very low temperatures. We are talking about at a temperature of -196 degrees centigrade. It is used to keep some substances at very low temperatures. Once it is liquefied, then it will maintain that liquid state so long as it is under enclosure, that's at that high pressure. It will maintain the low temperatures, making whatever has been kept in it to still be at that temperature at which it is existing. So at -196 degrees centigrade is at very low temperatures. So some of the substances that can be kept at that temperature is like semen from bulls, which is normally used in artificial insemination, which is so good in improving the flock of people. You have maybe a heifer which is not of a very good quality. You can still carry in semen from a better breed of a bull, artificially inseminate the cow, then whatever you will get out of that will be a better improved variety for maybe meat or milk, fat content, or whatever you are after. That is one of the biggest uses of nitrogen. But you also see that nitrogen is also good in the atmosphere, being that it is the gas that has the highest, or is the substance that has the highest percentage occurrence in the atmosphere of about 78%. It is very good at regulating combustion. So it is nitrogen that regulates combustion when anything is burning. Assuming a state where nitrogen is not existing in the atmosphere, then we shall be in problems. Once you light a point, then every part will catch fire because we have no regulator. So nitrogen being at 78% is a very good regulator of combustion. So you can still continue with the other elements, just as I've been going through these others. And the other elements include chlorine, magnesium, calcium. And remember, magnesium, calcium, sodium, and potassium were discovered by the same scientist by the name Sir Humphrey Davy. Then you also have aluminium, which was done in 1827. And lastly, helium. Those are the ones we talked about. So you can fill up the table as we are moving on. The second question is a bit mathematical in interpretation. Is we convert the percentages we are having here of how much oxygen is occurring in the Earth's crust, how much silicon is occurring, aluminium up to magnesium as the main elements. But remember, we also have our number 9, which is others. And the others we said is 1.5%. So we convert these, number 1, by making a pie chart. And from that pie chart, we convert it into a bar graph. So let's start with a bar chart. Now, as a bar chart, you can look at these in terms of degrees, because a bar chart requires you have to get a circular point. This is our center point. If this can be our first line, take 46.6 as degrees. Out of that, then you can comfortably cut out, probably by assumption, this one is giving us 46, and that is oxygen, 46.6. If maybe whatever you are using, that protractor cannot read to 1 decimal point, you can move to 0 decimal point such that maybe this one will make it 47. Remember, this is just an act of knowing how to manipulate. We may not be very much exact, but if yours can read up to that 1 decimal point, then the better. So if it can, take this one to be 47, because that one will be rounded off to 47. So as you continue, you will get silicon carries that much, and so on, depending on the levels of the degrees as you have done. Remember, the last one, which should be the smallest, will be others. This is our number 9, the others. The way of split is not as expected. Remember, I have not been measuring. So as an exercise, get your protractor and draw this pie chart. Now, after you have done this pie chart, convert this into a bar graph. What's the difference between a pie chart and a bar graph? The information they carry is the same, but the shape of the diagram will be different. For a bar graph, we have an X and Y axis, which will be well calibrated. Now you can have on the Y-axis the percentage occurrence, such that our highest is 46.6. So you don't need to go to 100. Just make sure that if this is our 0 starting point, then the highest point you can go to, probably you can make it to 50.0, because our highest point here is 46.6, so that you can get a very good well spread bars. Then on the x-axis, we can have now the elements. So you can have here the elements. Now with these elements, you will need to get each element at its particular point. Each element at a particular point. For example, I can take this first one. From here to here, I'm taking to be number 1, and that one can be oxygen. You can have the bars touched each other or separated. They will all give the same information. So if they are to be attached, and probably this is our 46.6 point of oxygen, you can shade it or use different colors to show out that this is oxygen. So maybe I can use this to show out that this is oxygen. Then the second element will be silicon, which was 27.7. So assuming that 27.7 is somewhere here, then this one is silicon, and I can maybe use this one to mark out my silicon. Then the third one was aluminium, which is 8.1, and maybe 8.1 is at this point where I can use this to show aluminium. These are bar graphs that are touching each other, but you can also split. In splitting, you have the same information on the y-axis and the x-axis. We are talking about percentage, and here we are talking about the elements. But you have your first one, oxygen, then leave some space, then have the second as silicon, some space, third one as aluminium, so that this is what will be seen. silicon, then our aluminium. So whichever bar graph you would like to use, they will all give the same interpretation. And also depending on the space available on the x-axis. If it is big enough, you can use this, but if it is small, then there's no way you can go in for this. And that is based on how many elements you are working with. Looking at this, they look so many, maybe you can go for the first one, where the bar graphs touch each other. That will be the exercise, and from that you can very fast interpret the graphs, whether pie chart, bar graph, and maybe the bar graph is much easier and faster than the pie chart to show how much oxygen is so big in the Earth's crust and how much the others, which is 1.5, is so small, because it will appear very small indeed. When you relate it maybe to how much oxygen is, then you'll discover surely oxygen is a lot in terms of occurrence. The other questions we may look at are general statements as we have been discussing about this. These are just general statements that we may just give a word, a statement in answering the questions. So this one will make question number 3, and the question is, what percentage of elements are metals? What percentage of elements are metals? So to get the percentage of metals, you just get out of 100%, we had subtract the percentage of non-metals. You can get out the non-metals, then you will get the metals. Alternatively, you can get the total of the metals. As you can see all of them here, get the total of 8.1, 5.0, 3.6, 2.8, 2.6, then lastly 2.1. Remember, we cannot include others because others means a mixture of the two. Even if we have something there, we shall just get the estimated percentage. The other question is, what is the most abundant element in the Earth's crust? And it speaks by itself. From our graphs here, you can see oxygen is the most abundant. And the other question is, what is the most abundant metal in the Earth's crust? Again, looking at the bar graphs, pie chart, or the table as it is, aluminium takes the mantle because it is at 8.1. And this explains why so many substances that are water resistant are being made from aluminium. Look at how many planes we have in the world, and most of them, their bodies are more than 70% aluminium. Reason? Aluminium is a strong metal and light. And one last question. What do we have internationally recognized symbol for elements? Why do we have internationally recognized symbols for elements? Why do you think we should take our time, the whole trouble of making sure we align a name and a symbol? This is our last question, and it's a very important question. Why we should have an internationally agreed name and symbol for all the elements? The answer is, different worlds, the different parts of the world have different languages, but they always encounter the same type of element. And all these people from all these parts of the world, they will interact at one time or another. Some information may be shared, which will still be carrying the same element in it. So for the 2 people, 3 people, there's so many groups. To understand each other, they must have a common way of calling the same element, of writing the same element, even if the language is different. For example, you will go to Germany, the element oxygen must just be written as O. You go to Britain, in English, it has to be written as O. You go to Japan, the same story. Reason being, that sand is in Japan, that sand is in Germany, that sand is in France, must always share things that are of the good for all the humanity. And they will be carrying the same coding of the elements. So we always use internationally agreed symbols for easier understanding, identification, and communication of scientific facts. The elements must always be well written. And maybe just to repeat, if an element has two letters, the first letter must be a capital letter and the second letter must be a small letter. Secondly, the two letters must not touch each other. And thirdly, the shape of the letters must agree. If it is small, it must be small by size and by shape. You remember I mentioned the issue for U and U when writing copper. This one is wrong and this one is correct. Ingali ngapi? Imeisha? I'm doing well. That marks the end of our lesson today. Until next time, thank you.